Welcome to the last set of lectures. Congratulations on surviving this long in interferometry. So we're going to start off with Ram talking a bit about polarization.
My name is Ram, and I hope you guys are all sufficiently caffeinated because it's going to be polarization time. So I've been working on polarization for a long time, and the SMA has been a key instrument for polarization. I think without the SMA, it wouldn't be a stretch to say that a lot of the ALMA observations you see right now would have taken place, because SMA was a pioneer. And this was one of the first objects we did. I'll talk a little bit about it later. This is, for those of you who may not know, this was done way back long time ago. So this is NGC 1333 RS4A. We'll get to this a little while later. Okay, so why do we care about polarization? So this is an outline, and we'll be talking about the polarization science. We'll be talking about Stokes parameters, how do you measure polarization, the response of an interferometer to polarized signals, the ideal response, and then the actual response and the presence of contaminations, things like instrumental polarization, and ultimately how you calibrate the polarization data. Okay, so why study polarization? Thus far, we've only been using total intensity. So that's Stokes I, that's it. But there are three other Stokes parameters, Q, U, and V, and so we'll talk about them later. So we've been ignore total intensity, but it's very important to study polarization. So even though 90%, 95% of the sources you come across will be all unpolarized, and that's fine, but it still matters. And there are some cases where it matters even for calibration purposes to know how polarization. But why do we care about polarization? Because polarization is a characteristic signature of magnetic fields. So wherever you have magnetic fields, there'll be some sort of polarization in some form. And so if you want to study magnetic fields in the universe, in the interstellar medium, near and far, you need to study polarization. So where are magnetic fields important? So one of my motivation to study magnetic fields was from star formation. So one of the theories states that magnetic fields are very important for star formation because you have a cloud of collapsing gas and dust, and magnetic fields can help to prevent this collapse and so on. So, but then how do you detect this magnetic field? It's very hard. But it turns out that if you have magnetic fields in a cloud, we've already talked about grains, right? So I think Jonathan was talking about dust grains, elongated dust grains. So if you have elongated dust grains in a molecular cloud or in a cloud, and these grains are spinning, then eventually they'll start to spin with their short axis to be more or less aligned with B. It's not a perfect alignment, but they'll start to get more or less aligned with B. So you would have the short axis aligned with B, and then the long axis is then perpendicular, and that'll be along the direction of the electric field. And so what happens is that you take an unpolarized star or something that goes through this cloud, and then the radiation preferentially tends to get absorbed in the long axis. And so with the so essentially the polarization that comes out is essentially perpendicular to this long axis or parallel to the short axis. And therefore the polarization in this case is perpendicular to the magnetic field. So it was used to study starlight polarization, to study polarization in clouds in the galaxy. And so now if you have polarization and absorption, that's what I've been talking about. In emission, you just reverse it. So in emission, the grains will tend to emit along the long axis of the grain, and then the polarized emission will be along the long axis. And then in that case, if you want to get the magnetic field, you rotate by 90 degrees. So a lot of maps, I'll have stuff is rotated by 90 degrees to get the magnetic field. Okay, so this is the model of a cartoon, simple model of star formation. It's a cartoon model, so it's you start with a cloud of gas and dust, and this cloud starts to collapse. And it turns out that magnetic fields can provide support against cloud collapse against the field lines. So, but through the field lines, the matter will collapse and form this disc-like structure. It's not really a proper disc, but it's like a large structure, a flattened structure. And then what happens is the magnetic fields only directly impact the ionized or charged particles, and the neutral particles can actually slip through the magnetic field and through. And eventually, what happens is that the magnetic field starts to get pinched, and you get this pinch structure, hourglass morphology of the magnetic field. And this was something that was really difficult to see because the polarizations typically are a few percent, maybe 1, 2, 3, something like that. And so you can imagine that this is something hard because David, Mark were discussing dynamic range, and typically we may have 50 or something, but we really need to get down much lower. So it's a hard thing to do. But with the SMA, we did this, and this is our RAS4A. And so we observed the magnetic field structure, and that does look indeed somewhat pinched. Problem is very, very far away. We don't have enough signal to noise to be able to tell what's happening in the cloud. And this is where actually things like larger single dish telescopes like JCFT are useful to provide this complete picture. But nonetheless, if you want to look at magnetic fields at high resolution, interferometry and polarization is the way to go. And so this was actually one of the first objects. There were a few other objects that we did. And so this was a low mass star forming region. We went ahead and did polarization of high mass star forming regions. This is my favorite high mass region, Orion. Very, very messy, very strong, but really messy. And actually, this map shows the polarization vectors or the vectors over at 3 different frequencies. And you'll notice that there's a 3 millimeter frequency and there's a 1 millimeter and the 0.87. Obviously, the SMA doesn't do 3 millimeters. Where do you think the 3 millimeter one came from? It came from BIMA. This was taken 25 years ago. And it's amazing that polarization, it works fine. So the telescopes, and I mean, I was a little bit skeptical initially, but it all works. And at multiple frequencies and multiple telescopes all show you the same result. So the system is really robust. The problem is it's a little bit messy to study individual objects like this. And so you've got to make a statistical survey. And Chijo led the survey at the SMA of high mass star forming regions. There are lots of postage-sized pictures. It's a little bit hard to see, but we did a bunch of high mass star forming regions systematically. And so once you do the systematic study, you can study properties in a statistical sense, like things like cloud orientation. Remember, I showed you this picture of this collapsing cloud and the magnetic field to be perpendicular to that cloud geometry. Is that something that we see? Is there a connection between cloud geometry and magnetic fields? Is there a connection between cloud orientation and magnetic fields? Then the one other thing that we did, and it's obviously the SMA is really powerful, is that you can do you can observe CO. And once you observe CO simultaneously and other molecules simultaneously, you can get the kinematics and dynamics in this object. And things like outflows and jets, etc. And then we can try to figure out, is there a connection between magnetic fields and jets, magnetic fields and outflows, etc. So this was a very rich data set, and it's something that the SMA had done in a systematic fashion. So these are local star forming regions, but initially though, the SMA polarization was built, the polarimeter system was built by Dan, when he was a graduate student, and he was working with Ray Blundell and Jim Moran. And he was not interested in star formation. Jim Moran was certainly not interested in star formation, but it was just Sag star. And so, in fact, Jeff is not here, but yeah. So Jeff was one of the pioneers of trying to do Sag star polarization at millimeter and submillimeter wavelengths. And so that was one of the reasons that the polarimeter got built. And so typically when you measure in polarization, the quantity that you're looking for is the electric field vector or the position angle or the planar polarization of the electric field vector. And that's what you try to measure. You measure other quantities like polarization fraction and things like that. And we'll discuss that later. But here is a study which shows a Sag star observed on different days with the SMA. And so this actually source is very variable in polarization. And so studying variability is important because it can tell you a little bit about accretion physics and other processes that are taking place. And so here you can see that Sag star, which is shown by these black points, this is total intensity. There's a lot of variation. And remember, quasars and stuff like that vary a lot, but Sag star varies a lot more. And actually that is a challenge to actually study that very well. But you can see that we have other quasars which don't vary as much throughout the day. So this variation in Sag star is real. There's some kind of flaring activity. But then at the same time, we can also study the variability in polarization simultaneously. And again, the black crosses at the bottom panel show you the polarization fraction. And again, that seems to vary, but maybe there's a correlation here. So when the flux density goes down, the polarization also seems to go down. But here the flux density is going down, but the polarization fraction is going up. So who knows what's happening? So again, we can use, it's a little complicated region, but the SMA has been a pioneer in getting systematic observations of Sag star. And we just heard M87. SMA was one of the first ones to do polarization of M87 at submillimeter wavelengths. And so this was at 1 millimeter. And so one of the things we can study is the rotation measure in such objects. And so this is the relationship for the rotation measure and the polarization position angle chi, which was defined earlier. And so if you plot the polarization angle versus lambda squared, that's what we're doing here. So we are plotting the polarization angle versus lambda squared because the SMA has a very broad bandwidth, and we can study the polarization simultaneously across different frequencies. And so then we can determine what the rotation measure is. And once we know what the rotation measure is, we can study properties like electron density, magnetic field strength, and then this leads us to figuring out accretion and other phenomena. And this is really important. We just saw what happened to the polarization. We don't have that result yet, but hopefully it's coming soon. So this is M87. So this is the total intensity image, but we don't have any magnetic field information yet. We don't have any polarization yet, but it should be coming soon, hopefully. Okay. So we've seen this picture already, and so typically we're interested in the electric field planar polarization, and that's something like this. So if you imagine if you're looking at this angle on this axis, and if you look at the tip of the electric field vector, you'll notice that it oscillates up and down just like this, and basically this is how it's going to look. So the electric field is oscillating up and down, and so this is when it's linearly polarized in this direction. So obviously you can have different forms of linear polarization. You can have linear polarization in this direction. And so again, this is the tip of the electric field vector. So this is vertical, this is horizontal. You can have 45 degrees. You can have any arbitrary degree. So this is just linear polarization, but then you also have circular polarization, and that can happen when you combine two linear polarizations with a delay. So if they're both linear polarizations are equal in amplitude and there's a delay of 90 degrees, you'll get circular polarization. And then that's how it looks. So if you look at the tip of the electric field vector, it's going to trace like a circle. And so one of these is left circular and the other one is right circular. It depends on your convention, depends on whether you're looking at the telescope or you're looking at the sky. So there's a particular definition, an IAU definition. That's important to know that because you can mess up. In fact, we were having troubles with the JCMT not too long ago because the polarization, we were trying to measure the polarization plate orientation. It turns out it was off by 90 degrees from what the convention is. So it's important to get that right. And so this is circular polarization and left and right circular polarization. In general, you'll have some sort of elliptical polarization if the amplitudes are not equal. So that's polarization. But we know, so it's very painful to keep describing, okay, this is vertical, horizontal, and we need to quantify this. And so what we use are the famous Stokes parameters. And the I is the total intensity. We've already studied that. And Q and U describe the linearly polarized intensity. And V is the circular polarization. So one of the things is obviously, and then if you have a source which is 100% polarized, and then in that case, this total intensity, Stokes I, there's a relationship between the total intensity and this. And so you only have 3 degrees of freedom in this case. But typically, most astronomical sources are only partially linearly polarized. And then we define a fractional polarization M. And then we can define a complex linear polarization quantity, P, which is equal to Q plus IU. I'm using I here, or it's equal to M times I times e to the I2 chi, where M is the fractional polarization, I is the total intensity. The magnitude of P is given by this quantity, and square root of Q squared plus U squared, and then the electric field vector, which was defined earlier, is basically half of tan inverse of U over Q. Now, this is very, very important. P is equal to Q plus IU. Try to remember that. Okay, so since we've done I've already shown you this picture. So it's for different cases. For example, if I have completely vertical linear polarization like this, then Q is taken to be positive. And then if you have horizontal polarization like this, Q is taken to be negative, and U is 0 and V is 0 in this case. And so the Q and U axis are not orthogonal to each other because there's a factor of two times in the angle. So U equals positive and Q equals 0 is an axis at 45 degrees. And U is negative in this case. And if you were to flip the other axis, you would get U positive. So this is something to remember. It's orthogonal, but there's a factor of 2. And for circular polarization, Q and U are 0 in this case, and V is negative for one case, and V is positive for the other cases. And in this case, this is an exercise, which I haven't done. But anyway, you can figure out what Q, U, and V are in this case. Okay. So since you guys have been doing very well so far, you've studied a lot of interferometry, you've seen a lot of equations, and so we can derive, go ahead and start to begin. I think there's plenty of time. We can start to derive what the polarization response is for an array. And so this is an arbitrary antenna, and for each antenna there is a polarization ellipse, and which is how much radiation is going along the x and y directions. Is there a difference in the phase between the two? So you will have in general some kind of elliptical polarization, and then you can take the EX and EY, and then take the other antennas EX and EY, and you can form all the four products, and that's how you do polarization. So this is one algebraic way, but it's a little bit painful, and if you see, we'll go through it right now. And then there's the matrix formalism, which is a little bit different, and it was done more recently by Hammaker, Bregman, and Salt. And they wrote down the polarization in terms of rotation matrices. You already know how to do that. So that's e to the j theta, which is cos theta plus j sine theta. And then we have the instrumental polarization or the leakage, which again can be represented by a Jones matrix. And then the gain terms, which you're already familiar with. So once we have that, we can go ahead and start to do the math. Is everybody ready? Okay, enough caffeine. So I think we can start to do that. So I think you should be able to do it in your head, but I don't think we have enough time. So you've all seen this, a miracle occurs. And that's how sometimes polarization seems to me. It's like there's a miracle, right? But anyway, so we'll skip this and assume that. So you can go and look in Thomson, Moran, and Swenson for derivations. So this is the ideal interferometer with linearly polarized feeds. And that's what is present in a lot of telescopes. They have feeds which are linear. The SMA feeds are linear by design, but we'll talk about some modifications later. And so you can form the four products. I showed you, right? It's X and Y are the two linear polarizations. And then if you have gain terms, which we've already talked about, then the polarization response is something like this. So in this case, so Q and U, remember, are the linearly polarized terms. There's an angle phi, which is the parallactic angle, and we'll talk about that later. So one thing to note is that for all of these correlations, there's at least two or more Stokes parameters. It's impossible to get an interferometer product to be equal to only one Stokes parameter. And that's something important, which means that in order to get the Stokes parameters, you have to do some more algebraic manipulation. For example, in this case, if you want to get I, you'll have to add these two and do some subtractions. Again, to get Q and U, you can start with these equations. And then if you want to get V, you can subtract these two. So to form the Stokes parameters, you have to do some more algebra on this, and that can be tricky. So this is the ideal response with linear feeds. So the ideal response with circular feeds is a little bit simpler. So in this case, you have just RR and LL, so the right and left circular polarization. And then the interferometer product is basically equal to I plus or minus V. And then for the cross terms, the left RL and LR products, the interferometer output is basically proportional to just Q plus IU. And then there's this factor, which is the parallactic angle. Again, we'll talk about that later. So this is a little bit more simpler than the other one. It's just proportional to two of these, and then it's much easier to determine what left, right, what the Stokes parameters are in this case. Okay, so in reality, things are a little bit messier. There's something called the leakage, which for those of you who are interested in polarization, your data will have the instrumental polarization is also called the leakage. And that's usually represented by these D terms. And so you'd have to remember that matrix I showed you with all the D terms. You can do all the algebra, multiply everything to get out, and that's how it looks, right? So this is your interferometer output for the four correlations you're going to get with circular feeds. So one of the things, though, is that typically the instrumental polarization and the linear polarizations for most of the sources you're looking at, or most of the calibrators you're looking at, is quite small. It's like maybe a few percent, 5% or something like that. So one thing you can immediately do is you can get rid of any products things which are products of two terms. For example, here is D1 times D2, or from the two different antennas. And so this is, let's assume, 5% times 5% is really small. And so we can ignore this. We can also ignore things like this. So D times Q and D times U, ignore. So there's a lot of simplification that you can do. And once you've all done all that simplification, you end up with something like this. So this is not too bad. So this almost looks like the right and the left almost equal to the ideal case, where it's just I plus V and I minus V. And then the right left and left right products are basically the Q plus IU. So that part looks the same. But there's this extra product. This is basically the instrumental polarization. So the SMA has normally linear feeds, but for polarization observations, we insert a quarter wave plate which converts a linear to circular. And the reason you do that is to get Q and U from this, you basically subtract these two. Assuming you can calibrate the instrumental polarization out, you just subtract right, left with left, right. But if you go back to the ideal linear feed equation, to get Q and U, you've got to subtract something like this, XX minus YY, and which means that you have something which is 100%, and so it's like some number like this over here, which is 101, and you might have a 99, and so you're trying to subtract 101 minus 99 to give you 2, and that can be a challenge. So it's easier to therefore observe, to observe linear polarizations, your feeds should be circularly polarized. And so to observe circular polarization, your feeds should be linearly polarized. And so it's a little bit counterintuitive, but that's what the algebra shows. Okay, so this is the equation that we have, and typically we have to solve for these instrumental terms. And so remember this parallactic angle, and that's really important. So it's a parallactic angle is basically, okay, so the parallactic angle is given for an alt-az telescope, an alt-az mount, which we talked about. Remember antennas from, I think, yesterday? So, so for an alt-az telescope, the instrumental polarization is fixed in the frame of reference of your antenna, whereas, or the frame of reference of the Earth, whereas the source polarization is in the frame of reference of the sky. So imagine a linearly polarized source which is rising. So it might have an angle like this, but then as it rises up and it transits, the angle is going to change. And that's what we use. So that's what's given by this parallactic angle. It's a function of the latitude, the hour angle, and the elevation. And this is a known quantity. But then at the SMA, we don't have an alt-az telescope, but we have like a Naismith mount. Then we have to modify the this parallactic angle by this formula. But again, we know all these terms. And so given that, we can plot that for different declinations, for different source declinations. And you'll notice that the maximum change occurs at around transit. So typically when you're making polarization observations, you try to observe a polarization calibrator around transit. So typically within a couple of hours is what you need around transit. It doesn't have to be contiguous, but it has to be strong enough. So typically, remember, we use the big four, any calibrator from the big four, 3C 273, 279, 84, and 3C 454.3. But with the expanded bandwidth, I think we should be a lot more sensitive, but maybe we can go down to sources which are not as strong. So that's what we do to obtain this. And so given the formula above, so this is how it actually, so this, we actually look at visibilities. So you can look at the visibilities in the real and imaginary plane. And so remember that equation I showed you. Okay, too much. Okay, so this equation, right? So it's Q plus IU e to the minus 2 I2 phi. You can expand this out in cos 2 phi minus I sine 2 phi, and then you can write this out. So you can, so basically this will vary in a circle, whereas this quantity will remain fixed. And so if you were to plot the visibilities, then in the real and imaginary axis, you will notice that the left, right, and the right, left visibilities trace a circle. The center of this circle, basically over here and here, is the instrumental polarization. And the radius of the circle tells you what the source or calibrator polarization is. So this is obviously a simplified equation. Real life is not like that, but you'll have something like this, but it's still good, right? You can even in this case, you can trace what that center of the circle is. So typically this is a calibrator which was about 5% polarized. You could even go down to 1 or 2% polarization and determine the instrumental polarization very accurately. So that was obviously a simulation, but in real life, this is 3C279. And so this I'm plotting, instead of plotting the parallactic angle, I'm plotting the hour angle. It's just the proxy for the parallactic angle. And so if everything is calibrated, the left, and the right polarizations are just I plus or minus V. And typically the circular polarization is really small. And so you'll have a phase of 0 anyway. And then the right, left, and the right, left, there's a phase variation because of the parallactic angle. And you'll notice this sort of structure. And so where these cross is where you can, from the crossing point, or you can essentially determine what the intrinsic polarization of this calibrator is. And so this is 3C279. You can do this for 3C273 as well. It's a little bit weaker, but it's still, you can notice this trend, right? And from this, you can see that these two are differently polarized. Okay. So, so there are a few specific things at the SMA. So at the SMA, normally you need receivers which are dual polarized by design. But the SMA, we don't have proper dual polarized receivers. What we have are two receivers which have orthogonal polarizations, and we cross the two. So these two have completely independent LOs and other systems, so it's an issue. But so we use the 230 and 240 in the 345, 400 sets, and we can essentially then get we can do polarization observations with that. As I mentioned, we have a quarter wave plate which converts the linear to circular. The wave plates are optimized for CO221 at the CO221 and the CO322 frequencies around about 230 gigahertz and 345, but they're fairly large bandwidths. And so we can use them all the way down to almost like 210 to about 245, 250 gigahertz. So it's quite good. It's very broadband. The instrumental polarization is very monotonic. And near the design frequency, which is around 230 and 345, the instrumental polarization is really low, about 1%. But then it can climb to about 5 to 7% at the edges. It's also very stable as well. And if you look at Dan's thesis, it's stable over time. And it can change, obviously, if you change receivers and other optics, then it can change. But if you don't change anything, it's quite steady. So the SMA antenna polarization, I'm not going to show you this, but it's actually quite good. And the SMA antenna is designed in a way that everything is on axis, and this leads to a very, very low polarization variability across the primary beam. And so this allows us to map all the polarization, the structures, all the way to the edge of the primary beam. For those of you who've done ALMA observations, there are restrictions on how much of the primary beam you can image polarization in. So as I remember the fact that this P equals Q plus IU, and remember David and others mentioned, and I think mentioned this morning that to get, so since I is real, the Stokes I normally is real, to get the conjugate point minus U minus V, all you have to do is to take the conjugate of the Stokes I, but the polarization is as defined is Q plus IU. So you really cannot, so to get P of minus U minus V, you can't just do the conjugate of that. So you actually need to make a separate measurement at this point. And so this is something that is a little bit esoteric, but it's why you need dual polarized receivers. You can't take the complex conjugate of P at that other point. And that's why it's important to have dual polarized receivers. So one of the things is with the SMA is that there are gain differences between the two feeds, left and right. And then there are passband and other things. So it's important to be able to calibrate that. There are some ideal specific routines which can do all this. But then, and since these two feeds, receivers are different, there might be phase jumps between the two, and that's important to calibrate that as well. So the polarization, most of the calibration is done in IDL for the gain, bandpass, flux, etc. But the polarization calibrations are not there in IDL, but we use Myriad to do that. So it's just one step which needs to be done in Myriad. And so once you have the calibration, then you can invert all four to get IQ, U, and B, and then you have to clean separately. So one thing to remember is that while I is usually positive for most everywhere, Q and U and V are going to be negative. So you can't put a positivity constraint when you're trying to clean images. So you got to clean both positive and negative. And then once you have the cleaned images, you can combine Q and U to get polarization fraction and polarization angle images. And that's it. And so I'm going to stop here. Thank you.
Questions?
Question. I want to comment on the source for RSOI. RSOI is my source for the master thesis, and actually Ron is also the cause of my paper, and we use the ALMA and GBA to detect that source, and actually we found that at the center of the broad star, the dust polarization is due to extinction instead of ignition, so it will have that the magnetic field direction will be misaligned with the outflow to align with the outflow. And I want to share that I will give a talk at EAO office at this Friday 2 p.m. So if you are interested about the dust polarization and the magnetic field, we can come to hear my talk. Thank you.
Yes. Good. Oh. Yeah, it's important, right? Polarization. So the magnetic field is only inferred. We don't have a direct measure from this linear polarization observations. To measure the magnetic field strength, I left this out completely because SMA, we don't do it yet, is to determine the magnetic field strength, you need things like Zeeman. And so with Zeeman, you're trying to measure the circular polarization because if you have a spectral line or something, let's say take CN, the various, so the CN transition, it depends on the magnetic field and you'll have a splitting of the lines and you can use that, and that depends on the magnetic field strength along the line of sight. And this effect is really small, maybe 0.5% or something like that. And so, so the linear polarizations typically we're trying to measure are maybe a few percent, 2, 3, 5%, but this is something which is even harder. And it's very important to do that, but I think we're not there yet.
A quick question. On your previous slide, you mean that to do polarization observations, you cannot use 230 and 345 at the same time, right?
Yes, you cannot do. So yeah, because we need both receivers to be tuned to the same frequency, and yeah, we cannot do that. I mean, yeah, not right now. Yeah, but I think we have a future. Whenever we get the new, so we are working on a new cryostat design and a new upgraded WSMA, which we have not talked about at all. Eventually, in the next few years, couple of years, we'll get that, and we will have something like a diplexer. And then with the diplexer, we'll be able to, it depends. They'll be lossy and stuff. And I mean, you have to have a reason why you want to do it. Is there a particular reason why you need to do the 230 and 345 simultaneously? Yeah, because, so if you have a reason that you need to do it simultaneously, then obviously. But the thing is that the SMA is broadband enough that the wave plates actually work very well across the band. And so if there's something like Faraday rotation, that you want to measure, you can do that fairly well with the SMA. But there might be some cases where, yeah, it would be good to get a larger frequency coverage.
Yes. All right. So in the interest of time, let's cap it there and thank Rob again.